Today we're going to conclude this chapter on approximation algorithms. So, last time we talked about approximation algorithms for the traveling salesperson problem, more specifically for the metric traveling salesperson problem, where there's a promise that the weights assigned to the edges of the graph, complete graph, but some edges have very large weight. And the promise is that these edge weights, satisfy the triangle inequality, which means if we take a detour, then the weight of this detour can be no shorter than the weight of the direct edge, which makes sense. Right? And we discussed two polynomial time approximation algorithms for this problem. We cannot expect to solve this problem exactly, since the underlying decision problem is NP complete. We will return to that at the very last slide of today's lecture of this chapter. And the first approximation algorithm we discussed was the double tree algorithm, which is also known as twice around the tree. And it's called it that way because it first calculates a minimum spanning tree, which we know can be done in polynomial time. And then walks around that minimum spanning tree, passes through every edge twice using this in-order traversal. And then we estimated with these three estimates, rho and 1, the weight of the total weight of the minimum spanning tree is no larger than the weight of the unknown optimal tour. And then we made two further estimates and combined, we concluded that the total weight of the tour output by the double tree algorithm is no larger than twice the total weight of the unknown optimal tour. And I originally wanted to have a mini quiz where you manually execute this double tree algorithm, where the first step is already finished. This is a minimum spanning tree indicated by the fat edges, and the rest are thin edges. So the mini quiz would have been execute the double tree algorithm on this weighted graph by performing the in order depth traversal on this minimum spanning tree with the shortcuts to avoid visiting edges or vertices twice. But in view of the time, this is not going to be a mini quiz, but instead this is your homework, part of your homework assignment number 6. So that was the double tree algorithm with a guaranteed approximation factor of 2. And then we improved that. Well, not we, but Nikos Christofides had improved that, also starting with a minimum spanning tree, but then adding some further steps to achieve guaranteed approximation factor 1.5. So in the end, also uses this shortcutting, calculating a Eulerian circuit, which we know can be done in polynomial time, and then converting that into Hamiltonian circuit, which in general we cannot do, but this is a complete graph. So, and the way to convert a Eulerian circuit into a Hamiltonian circuit in a complete graph is by taking shortcuts, avoiding vertices that have already been visited. And by triangle inequality, this will only make the overall path shorter. But in order to guarantee that there is a Eulerian cycle, we need to make sure that the graph on which we calculate a Eulerian cycle has a Eulerian cycle, and both sufficient and necessary conditions that every vertex has even degree. Now, the minimum spanning tree in general does not have all vertices of even degree. For example, the leaves have degree 1, which is odd. So the idea of Christofides is to add some edges to this minimum spanning tree to make sure that every vertex has even degree. And the way to do this is to calculate a minimum weight perfect matching among the vertices of odd degree, adding that to the minimum spanning tree, and thus increasing the degree of every odd vertex by 1 and making the degree even. And there's a famous known algorithm, the Blossom algorithm, for calculating minimum weight perfect matchings. And why calculate a minimum weight perfect matching? This becomes clear when we analyzed the Christofides algorithm. So here's Christofides algorithm illustrated. This was the late Nikos Christofides, born in Cyprus and passed away in London. And the idea is, so we take this minimum spanning tree, we identify the vertices of odd degree, and then we add a minimum weight perfect matching among these vertices of odd degree. Again, the question arises, why does there even exist a perfect matching? Not to mention a minimum weight perfect matching. And that's because, well, in a complete graph, here's a complete graph among the vertices of odd degree. There's an even number of vertices of odd degree. That's the handshake lemma, also an item in the homework number 6 that you're asked to prove. Handshake lemma. So that guarantees that such a perfect matching always exists. And then we proceeded to the analysis. So it exists. Then we proceeded to the analysis. For the analysis, we would consider unknown hypothetical shortest traveling sales tour like this. And then, for sake of analysis as a thought experiment, in this tour, mark the odd vertices from the minimum spanning tree. Yeah, the first inequality is the same as with the double tree algorithm. And then mark the vertices of odd degree in the unknown optimal tour. And then subdivide this optimal tour into segments between these vertices of odd degree. And here, every second segment we've drawn marked in green, and every other segment we've drawn in red. And these segments give rise, they're pairwise disjoint, right? And they connect all vertices of odd degree. So when we transfer these segments back into the minimum spanning tree, they give rise to perfect matching among the vertices of odd degree. In step number 3, Christofides has calculated a minimum weight perfect matching. The green edges form some perfect matching, and therefore the weight of the green edges will be larger or equal to the weight of the minimum weight perfect matching in step number 3, which is important for the analysis. Christofides considers also the segments in the optimal tour, every other segment here drawn in red. And here the same argument applies. The red edges will constitute perfect matching among the odd vertices. The edges are pairwise disjoint and all odd vertices are covered. and we transfer that red matching back into the minimum spanning tree, this gives rise to another perfect matching, which again can have weight no less than the minimum perfect matching calculated in step number 3. So now we have 3 perfect matchings in the minimum spanning tree among the vertices of odd degree. The minimum weight one calculated in step 3, denoted by M in blue. The green one, which is not necessarily minimum weight, but which comes from the unknown optimal tour, denoted by green M star. And also the red one, denoted by red M star, which also comes from the unknown optimal tour. And what we can tell by the definition, step number 3, that the blue one has weight less or equal than the green one, and has also weight less or equal than the red one, and therefore it has weight less or equal than the minimum weight of the green M star and the red M star. On the other hand, the green and the red M star constitute or arise from taking shortcuts in the unknown optimal tour, and by triangle inequality, taking shortcuts can only decrease but not increase the weight. So adding the length, the weights of the green perfect matching and the red perfect matching together can be no larger than the weight of the unknown optimal tour. Triangle inequality. And as I just said, the weight of the minimum weight perfect matching from step 3 will be no larger than the green one and no larger than the red one, therefore no larger than the minimum of the two. And now, since the two, green and the red, add up to the total optimal tour, at least one of them will have weight less than equal than half of the weight of the total tour, which means the minimum is weight less than half that weight of the total tour. And then, putting things together, the Eulerian circuit, the edges are edges that belong to the union, the multigraph of the minimum spanning tree and the minimum weight perfect matching. Therefore, they have weight less or equal than the sum of the two weights. And the Hamiltonian circle in turn is based on the edges in the Eulerian cycle with introducing shortcuts. So that weight is also less or equal than the weight of the Eulerian circuit. And then putting things together, that means the weight of the minimum spanning tree is less than the weight of the optimal tour. The weight of the perfect matching is less than half the weight of the optimal tour, and therefore the weight of the circuit output is less or equal than 3/2 or 1.5 the weight of the unknown optimal tour, which proves the approximation factor 1.5. Okay. Yeah, so that was Christofides, and then we proceeded to Knapsack. Knapsack is kind of like 3 problems, right? Input is always some packets with non-negative integer values and non-negative integer weights. And then we have the 3 variants. One variant is where there's a bound, how much knapsack can carry as weight. And we want to maximize the value. We want to pick packets such that the total weight picked still fits into the knapsack, but the total value of these packets should be largest as possible. So maximize subject to the constraint an upper bound on the weight. Adding the weights should be no larger than capital W, where capital W is also an input. That's Knapsack as maximization problem. Then except comes also in a variant as a minimization problem. Here, instead of an upper bound on the weight, we have a lower bound on the value. And we want to put that much value into the knapsack, but make it as light as possible. Minimize the weight subject to the lower bound on the values. Second variant of the knapsack problem. These are two optimization problems, one maximization, one minimization. And output would be either the maximum value or the selection of packets that attain this maximum value while satisfying the weight bound. And the other is the minimization problem. Output would be either the weight we obtain or the choice of packets chosen to attain that weight while satisfying the value lower bound. And the third variant is as a decision problem, not optimization anymore. In the decision variant, we're given both bounds. And the question is, can we satisfy both bounds? Is it possible to choose packets such that they obey the value lower bound and simultaneously the weight upper bound? Yes or no is the answer here for a decision problem. And the decision problem is well known NP-complete. So we cannot expect to solve it in polynomial time, but of course there's no proof to that beyond being NP-complete. We cannot approximate reasonably, we cannot reasonably define what it means to approximate a decision problem. So, but the optimization problems we can try to approximate. When we try to approximate a maximization problem, we try to get as close as possible from below to the maximum. When we try to approximate a minimization problem, we try to get as close as possible from above to the unknown minimum, up to some factor, which is the approximation factor. Two different variants of approximation factor depending on whether it's maximization or minimization problem. And we ended last lecture by describing and analyzing an exact parameterized algorithm for the knapsack problem using dynamic programming. So we introduced these abbreviations for a subset of the packets. W denotes the total weight of these subset of packets. Small v denotes the total value of this subset of packets. And our goal was to solve the maximization problem. So to calculate v or v star. And to this end, we conceived this table where the second parameter m says we consider not all packets up to here, but only packets up to m and subsets of these packets up to m. And here's the table. So the columns indicate how many packets we have considered so far. And at the end of the day, we want to consider all packets. So we're interested in the last column of this table. And the goal is to fill that last column by first gradually filling the previous columns and the previous rows. We're interested in the last row, the last entry in the last column. And the last column has this monotonicity property. Well, any column has this monotonicity property. By definition of the table entries, the table is kind of solves the minimization variant. So the definition is we want to achieve weight v, where V denotes is the row of the table. What is the least weight that we need of the packets in order to achieve this value? So we want to solve the maximization problem, but in the dynamic programming approach, we actually solve the minimization variant. And then by the very definition, we can read off the answer to the maximization problem by checking, when is the first time that the weights here increased, the least weight to attain value V? When is the first time that these entries in this last column exceed the weight bound capital W? We cannot go beyond the weight bound, so the last entry before exceeding capital W, that's the row number, and that's the one we read off, and that's the value we can attain while satisfying the weight bound. So once we've filled that table, then we're basically done. And filling that table turns out to be surprisingly easy. Filling the left column and filling the top row, that's kind of the initialization, is easy. So the top row is that where value is 0. And in order to attain value 0, we need no packets, no weight. So that's 0. And filling the leftmost column, similarly, in order to achieve value, positive value, non-zero value, among the first 0 packets, it's impossible. So the maximum of an empty set is, by convention, equal to infinity. Because, remember, without loss of generality, all packets we consider have strictly positive weight and strictly positive value. Those packets which have weight 0, we just put into our Knapsack by default and then ignore them. That's kind of the pre-processing. And similarly, those packets which value 0 are discarded, so they get done just Chosoyo. So after that, we only have packets with positive weight and positive value, and among them, to achieve positive value with packets, non-packets, it's impossible. And then come the induction step. We consider one entry in the table. And remember, the meaning of the entry is, what is the least weight needed among the first M packets to achieve value V? And there are 2 possibilities. So this is kind of the next packet, number M, that we consider and either include it or not include it. And we will include it or not include it depending what is better. So look at what if we do not include it? Then among the other packets, what is the least weight we need in order to achieve value V, not counting the next new packet number M, or putting that packet number M into the knapsack, then we don't need to achieve value V anymore because the packet number M already has been added. So now we only need to achieve value V minus the value of the packet M. But also, we've already added weight to the knapsack. So now the minimum weight among the other M-1 packets must be added to the weight of the packet we've just inserted into the knapsack. And whichever is better. We cannot tell in advance, but that's the whole point of filling the table. We can calculate the entry here by looking at the column to the left, right, from M to m minus 1, that's one column to the left, and then checking in the same row, row V, or looking into row V minus Vm, which is somewhere upward. So in this way, we can gradually fill the table from left to right, from top to bottom, by looking at entries to the left and looking at entries to the left and up, further up. So this is kind of a double induction, if you like, but basically it just means two nested loops, one from left to right, outside, and an inner loop from top to bottom. And in each step, inside the body of the two nested loops is look up to calculate the minimum of two entries and store that in the table. So that's basically constant time. So what is the running time, overall running time of this algorithm? It's the size of the table, right? Outer loop from 0 to n, and inner loop from 0 to the unknown v. And that's the thing, right? The running time, yeah, so that's how we add an entry in this table, and the running time is basically the size of the table, polynomial in n, the number of columns, and in v, the number of rows. And we stop when we have reached the row where the weight, capital T, the entry here, just exceeds our weight bound capital W. And how long does that take? How many rows do we need? Well, that depends on the value that we finally output. V is the value that we finally output. We don't fill the table beyond that. There's no need to do that. But when we measure the worst case analysis, the possible value of capital V, it depends on the binary length of the input. Binary length of the input means binary length of our packet weights. Then we might have few packets, which means n is small, but they could have very large value compared to their binary length. Keep in mind, the binary length is the logarithm of the value. And so put differently, the value can be exponentially large compared to the binary length, which means that the running time of this algorithm is not polynomial in the binary length of the input, because V, the output value, is not polynomial. The binary length of V is polynomial in the binary length of the input, but the value of V itself is not. So this is not a polynomial time algorithm, but it's dynamic programming, and it's the basis to our next slide, where we use this to turn that into an approximation algorithm. So that's what we're going to do next. Approximate the knapsack problem. Keep in mind, this is our running time bound. And this running time bound is good when capital V is small, whatever that means. So, yeah, we're trying to approximately solve the maximization problem instead of exactly. We're going to try to trade running time for approximation quality. Yeah, intuitively, the better we want to approximate, the more running time we're going to need in order to approximate exactly with no error. It's going to be exponential time. But it turns out that there's a trade-off. If we allow for less than the perfect maximum, then we can improve the running time from exponential to polynomial, subject to the weight bound. So to this end, let's recall this notation. this is a maximum value we can achieve among the packet values, small v1 up to small vn, subject to the weight constraint here. This is the weight constraint. This is the value we can achieve for a suitable subset. And the largest possible value we can achieve, that's what we want to calculate. That's the output of the hypothetical exact algorithm. Now we want to approximate that. What we're going to do is, this is a new method. Well, no, it's an old method, but new in this lecture, the scaling method. So the idea is the following. We take the packet weights and don't modify the weights. We take the packet values and we scale them down. Why is that a good idea? Because if we scale down the values of the packets, then also we scale down the optimal value that can be achieved with these unmodified weights. When we scale down the optimal value, then our dynamic programming algorithm will become faster, right? But the thing is, the values must always remain integers. Remember, our table in the dynamic programming had one row for each possible output value, and that only makes sense when the values are integers, not fractions. So that's why we not only scale down the values, but also need to round them to integers, and we're going to round them down. So what's the intuition behind that? Let's say we have the knapsack problem, and we have some weights given in kilogram, and we have some values given in 1. Values given in 1 give rise to very large numbers, right? Integers, but very large, right? I mean, like 10,001 or 100,001, or some diamond would be 1,000,001. That's a large number, right? So what we're doing here, we're rounding it down to maybe to John 1, which corresponds to choosing k equal to 1,000. So anything that would previously maybe have cost 9,999 won, after rounding down to John 1, would be good John 1, rounding down, okay? Always rounding down. Or even round it down to Gongman 1, okay? So what happens when we run our previous algorithm or look at the problem after this rounding down? Well, since we don't change the weights, the optimal value will also go down, right? If we multiply all values by 5, then also the optimal value will go up by a factor of 5. If we scale everything down by a factor of 5, then also the optimal value will go down. But since we round down, it could actually go down a little bit further than a factor of 5. Right? So we not only scale, but we round down. So that means if we now run our dynamic programming to calculate the optimal value in terms of John 1, and then multiply it back with 1,000 to recover the original amount in 1, then we can do this in time polynomial in n, the number of packets, plus the optimal value divided by k. So 1,000 times faster, that's good, right? But the result, the output of this algorithm will be worse than the optimal value, because remember, a packet which used to be worth 999.1 was rounded down to Gongchon 1, right? So this rounding down really incurred a loss. Our algorithm is faster by a factor of k, factor of 1,000, but it doesn't return the optimal, it returns something less. Yeah, we cannot get up to the optimal. The question thus remains, for the sake of analysis, how much smaller will be the result after this scaling down? And this is the crucial inequality. So we scale the values down, we round them down to the next lower integer, calculate the optimum, and then scale them up again, which recovers almost everything except for the part with the rounding down. How much does the rounding down part affect? In the worst case, when we round down, we lose a little bit less than k. You lose at most Gu1, right? A little bit less than Son 1, the worst case. For each packet. Now, if we calculate the optimum, and each packet we have made due to our rounding Son 1 cheaper than originally, then our output would be at most n times Son 1 less than the optimal output. That's the second inequality. By making each packet hypothetically Son 1 cheaper, in the worst case, all packets would have fit into this knapsack. So would have, in calculating the optimal solution after that, would be a loss of n times Son 1, n the number of packets. So that's the two crucial inequalities. The value that we output is at least the optimal value after decreasing the value of each packet by Son 1, and the optimal value for each packet value decreased by Son 1 is at least the optimal value before the price tag adjustment minus n times Son 1. And then this equality is just reformulating that, right? So 1 times the optimal value minus n times k divided by optimal value times optimal value. Now you see this is almost what we need for an approximation factor. This is what we output, which is greater or equal to some 1 minus something, that's an approximation factor, times the unknown optimal output. So now let's estimate this part, and let's choose k. Remember, we still get to choose k. Always said k is equal to 1,000, but we can choose k, right? This is where the trade-off comes in. And how are we going to choose k? We're going to choose k depending on how small we know that V star is. Now remember, without loss of generality, all packets have positive weight and positive value, and therefore, yeah, and each packet has weight, at most the weight bound. Why is that? What does that mean? It means if one of the gifts is a bulldozer, very valuable, really, really. But it certainly doesn't fit into my backpack, right? So we're going to discard the bulldozer or anything else whose weight as a single present wouldn't fit in anymore anyway. So that means the remaining packets which we have not yet discarded, at least each single one would fit in by itself. So the weight would be at most capital W. And that means the optimal value will be at least the maximum value of all the packets. We can always put in the packet with largest value because we've already discarded all packets which would not fit in even singly into the knapsack. And that means that we have these bounds on the unknown optimal value. In the best case, all of them fit in. But in the worst case, yeah, the optimal value will be at least the average of all packets. Or put differently, yeah, n times the optimal value will be at least the sum of all packet values. So that means we have kind of this bound here. And this says we can choose this choice for k. The sum of all packet values divided by n squared. If we choose that for k, then one n is cancelled. Another n here is cancelled here. And the v star cancelled. In the end, we obtain that this expression is at least 1 minus epsilon for the given parameter epsilon times the unknown weight. And here we have our approximation factor, right? So the output of our algorithm is at least 1 minus epsilon times the unknown value, where epsilon is now an arbitrary parameter. Given the parameter epsilon, we can easily calculate the sum of the values divided by n squared and thus obtain the value of k. Almost, because remember k must be an integer. So we still need to round this expression to obtain the actual value of k, but that's peanuts. So to conclude, for every given epsilon, we can approximate the knapsack maximization problem up to factor 1 plus epsilon in time, which is polynomial. Remember, running time is polynomial in v divided by k. K is this. So it's v divided by epsilon and, yeah, this running time. Where's the algorithm, you might ask? Reasonably enough, I didn't show you the algorithm. I'll leave it to you to turn this into an algorithm. What else can we see here? The smaller epsilon gets, the better quality we want, the closer we want to the exact. Exact means approximation factor 1 with epsilon equal to 0, right? And the closer we want to get there, then 1 over epsilon becomes large and the running time becomes also larger. But for fixed epsilon, the running time is polynomial in n. That's what we want. And this is what is called an approximation scheme. So let's recall about the metric Turing salesperson problem. We had 2 algorithms. One to achieve approximation factor 2. If we want a better approximation factor, we need a different algorithm. If we want an even better approximation factor, that's a huge open research problem. Can do a PhD thesis if you like on this question. 2 different algorithms with 2 different approximation factors. For the knapsack problem, the situation is very different. The knapsack problem, we can approximate up to any desired factor arbitrarily close to 1. And even more, this is called an approximation scheme. Getting any desired approximation factor. Even more, the running time, this is kind of like a family of approximation algorithms, one for each epsilon, right? The running time of this approximation algorithm is polynomial in n for any epsilon or 1 over epsilon. This is called a polynomial time approximation scheme. Even better, this is not really a family of algorithms, one for each epsilon. It's one joint algorithm that can deal with any given epsilon. Epsilon is part of the input. So if we want a better approximation factor, we don't need to switch to a new algorithm. We just use our algorithm and give it a different, smaller epsilon. And it will do that, maybe slower, but it will do that. And the running time will be polynomial not just in n, but in n plus 1 over epsilon. And this is called a fully polynomial time approximation scheme. Okay, approximation scheme means we can get approximation factors arbitrarily close to 1, polynomial time, and fully polynomial time. Okay. So that's the good news about the knapsack problem. Is this always possible? Can we always approximate NP-hard approximation optimization problems? No, we cannot. That's the last slide of this chapter. So buckle up, and then we're going to be done for this semester. So last theorem, we cannot approximate the non-metric traveling salesperson problem unless P is equal to NP. Of course, when P is equal, if P is equal to NP, then all these considerations become meaningless, right? Then we can solve all these problems exactly. But if P is different from NP, then provably we cannot approximate the non-metric traveling salesperson problem up to any constant factor, not up to factor 2, not up to factor 1000, not up to any desirable factor. So the two algorithms we considered really need this triangle inequality, not just in the proof, but also it's inevitable. And the proof is by contradiction. We suppose there is an approximation factor C, a constant, and suppose there is a polynomial time algorithm A, which approximates the general non-metric traveling salesperson problem up to this guaranteed factor. And now we're going to play adversary again, right? And use that algorithm to solve an NP-complete decision problem, right? This algorithm A is for the minimization problem, non-metric TSB. And we're going to use that to solve a decision, NP-complete decision problem, namely the Hamiltonian circuit problem. Remember what is Hamiltonian circuit? In Hamiltonian circuit, we're given a non-weighted, non-complete graph. Traveling salesperson problem, we're getting a weighted, complete graph. Hamiltonian circuit, not complete graph, some edges are missing. No weights, only yes and no question. Does this graph admit a Hamiltonian circle, which means a tour which starts at some vertex, visits every other vertex using only the edges that are allowed, and then returns to that edges, to that vertex, yes or no? Decision problem, NP complete. So here you see the two problems for your courtesy, for your convenience recalled. Traveling salesperson, complete graph with weights, Hamiltonian cycle problem, not complete graph without weights. Now we use the algorithm A to devise a polynomial time algorithm B for the Hamiltonian circuit decision problem. Typical kind of reduction, except if you take my course Theory of Computation CS422, reduction is defined for decision problems only. This is technically not a reduction, but the idea is of course the same. So what does the algorithm B do? It takes the non-complete unweighted input graph and turns that into a complete weighted graph on which it then runs the hypothetical algorithm A. How does it do that? Well, for every edge that is already in the graph, it defines edge weight 1, small integer edge weight. And for every edge which is not in the input graph, well, it must create a complete weighted graph. It adds an edge, but it gives that edge very large weight, specifically n times c. Remember, c denotes the purported guaranteed approximation factor of the hypothetical algorithm A, and n denotes the number of vertices of the input graph. So you can easily calculate n times c and assign this weight, and that can be done in polynomial time in the number of vertices. That's it. So here's the example. Let's suppose the input to the algorithm B is this graph, which obviously has no Hamiltonian cycle. And the algorithm B will introduce edges to this graph and edge weights. Black edges have small weight 1, and making it a complete graph, yeah, it's still some edges are missing, but the edges it introduces, the red ones, get very large weight. So that kind of, it is possible you can use these edges for doing a Hamiltonian cycle, but it costs a lot using only even one of these red edges. More formally, if the original graph has a Hamiltonian cycle, then the new weighted complete graph also has a Hamiltonian cycle, which uses only the original, the black edges of weight 1, which can add up to weight n. Since it's a Hamiltonian cycle, it traverses, visits every vertex once, and therefore traverses a total number of n edges of weight 1 each in this new total weighted graph. However, and yeah, by hypothesis, the approximation algorithm A then finds, since it contains a Hamiltonian cycle of weight n, the approximation algorithm with factor c will find a tour whose weight is at most factor c larger. So its tour weight will be at most n times c, by the guarantee of being c factor approximation algorithm in polynomial time. Whereas if the original graph, unweighted, non-complete graph, does not have a Hamiltonian cycle, then that means in the weighted complete graph, any Hamiltonian cycle must use at least one edge, one red edge, and of course at least n minus 1 other edges, so that the total weight of any Hamiltonian cycle in this enhanced graph will be at strictly more than n times c. So that from the output, even of the approximation algorithm, we in our algorithm B can recover and can deduce logically whether the original graph had a Hamiltonian cycle or not. If it has, then the approximation algorithm will find a circle of small weight, because even if it's only approximate, it will be no more than a factor of c more expensive than the least minimum weight Hamiltonian cycle. Whereas if the original graph did not have a Hamiltonian cycle, then any Hamiltonian cycle, and in particular any one output by the approximation algorithm, will have weight strictly larger than n times c. So by checking the output of the approximation algorithm, we and the algorithm B can distinguish these two cases and therefore can recover whether the original graph had a Hamiltonian cycle, a decision problem in purported polynomial time, which is a contradiction, since we suppose that P is not equal to NP, contradiction that algorithm A approximates in polynomial time the traveling salesperson problem non-metric. This is non-metric, right? You see why this is non-metric? Because traversing that red edge is more expensive than going all the way around. That's how expensive we made that red edge, but also it means it violates the triangle inequality. So that's the end of chapter 8 on approximation algorithms. We started with some motivation. Why do we consider approximation algorithms? We classified approximation algorithms, maximization, approximation factor, minimization, approximation factor. To discuss the metric variant of the traveling salesperson problem, double tree algorithm with approximation ratio, execute it manually. Christofides algorithm with a better approximation ratio 1.5. And we discussed the knapsack problem. We solved it exactly using dynamic programming in parameterized polynomial time, where the parameter, which may be exponential, the parameter is the value that is output. Not the binary length, but the actual value that can be achieved in this maximization problem. And then we applied the scaling method, scaling and rounding down, which accelerates the dynamic programming algorithm because it's parameterized runtime. And we analyzed how much just that scaling and the rounding, that's the difficult part, the rounding to integer, back to integer values, how does that affect the unknown optimal value? And then we determined how to choose the scaling factor k in order to achieve any desired approximation ratio 1 plus epsilon, which was then an example of a fully polynomial time approximation schemes. There are also other non-fully polynomial time approximation schemes, but this is not a subject of this lecture. And finally, we discussed that limits of approximability, the non-metric traveling salesperson problem, provably cannot be approximated up to any constant factor unless P is equal to NP. Okay, so I'm gonna stop the recording for now.